All right, so now we're going to discuss the resonance, having already covered the Thomson and the Rayleigh limits, and given a basic explanation as to why our sky is blue. I did first want to mention, if we don't really want to count the Earth's atmosphere as an astrophysics application, perhaps we should. Rayleigh scattering are typically then important in cool gases. Remember that Thomson scattering was important when we had a lot of ionization, so typically in hot gases in astrophysics applications. For example, Rayleigh scattering is the opposite, such that it's important in things like the atmospheres around very cool stars, so M stars, those that are cooler than our sun even, but also in exoplanet atmospheres, for example, can be an important opacity source, analogous then, of course, to our Earth's atmosphere. Anyway, now we're going to do the resonance case as, in my own opinion, a very interesting application here. Now, that's, of course, given by this when the frequency is almost the same as the resonance frequency of the system. It is custom now to work with actually an approximate expression where we use this expansion. Well, this one is exact, of course, nu plus nu 0. And then we say that whenever we have a difference, we have to take that into account. Otherwise, this would just be 0, right? But since the frequencies typically are very large numbers, then we can approximate this by just 2 nu, or alternatively 2 nu 0. And sometimes we will use nu, and sometimes we will use 2 nu 0 there. So that's just an expansion of that. We write again the cross-section. This is the expression we had before. Nu squared minus nu 0 squared plus omega nu squared, right? And now we just use this one in that, okay? And then we just rewrite this, and you can fill in the blanks here yourself. There's 1 or 2 algebraic steps only. I'm going to go directly to the point here today. And that is writing this as in this form. Nu minus nu 0 squared plus gamma 4 pi squared. So, and hopefully it will be evident in a while why we're writing it in this form here. Okay, so to make some further progress now, we need some information about this damping constant, okay? And for that, we're going to set that the work done here, which is then the damping force work times the velocity, so that would just be c hat, is just equal to minus the power lost. And that was just E squared c, and then we had c dot squared. So that's the work, and we set that equal to the lost power. And then we integrate this over one cycle of this oscillation, okay? So, numerically then, we set that damping times c dot, 0 to 1 cycle t, integral over the t is equal to minus well, 2/3 e squared cubed, and the integral t, and then we have a square there, right? So we can write this as c dot dt. Okay. And so what do we want to do now? That's a good question. Well, we're going to look at the right-hand side there. And then, of course, we know, since people have done this before, that let's integrate this by parts. Yes? This? Yes, because it's a square there. Remember that in the Larmor formula for the power, which is what we equate the work with, the lost power, we had the acceleration squared. Okay? So therefore we have a squared. But now I'm writing it this, and I'm doing that because I want to integrate it by parts. Okay? So we're going to have to either remember our integration by parts formula, ask ChatGPT or your favorite AI assistant for it, or we could actually do it from scratch, but okay, that's not, again, the focus here of this purpose of this course. So we integrate one and we let the other stand. We integrate one, we let the other stand. And then we take minus the integral over the integrated one, we let it stand, and then we take the derivative of the other one. C dot 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 dt. So that's our integration by parts. Yeah? And then we realize that, okay, this is sort of the same as we have had many times now. It's probably easiest to see if we put this now, our trial solution, on, again, just some cosine or some sine, sine omega t. And then when you take this, 1, c dot, you just get the cosine, you get out the t, you get out an omega, and you get a cosine omega t, and so forth. So actually, this again then is an uneven, and we're integrating over a whole interval here, so, and over a whole period, raised to 2 pi, it will become 0. So this one is just 0. So we're left with here now this integral there, which is just minus that and then minus this one. So it has a positive sign on this side of the equation. Okay? So we're going to move that positive sign over to this, and we're going to see that, well, we do have a c dot there, we have an ft, so we can actually now take this, take out the damping force. No, we cannot take out the damping force, we can take out c dot. Then we have the damping force there, right? And then since we have the positive, this must be a negative on the other side. 2/3 e squared c cubed c dot 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 dt. Okay. Now the thing, of course, here is that these are both then the same order. You know, there's 2 in between. They won't cancel. So the only way this integral now is always going to be 0 is for this to be 0. So we have identified our damping as 2/3 e squared c cubed c dot dot dot. Okay? And remember, in the beginning, we wrote this as minus m gamma c dot. Okay? That was what we set our ansatz in the as a damping force. So now, of course, we can just write down a expression for gamma as negative 2/3 e squared c cubed. We're going to have an m coming down, and then we're going to have a c dot 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 divided by c dot. And here is where I said before that, well, actually, we're going to use this property of the oscillating system that you take the derivative of, and then, of course, 1 omega always comes out. Okay? So do this yourself, and then you will see that this indeed, if you have an eigenfrequency, omega 0, we're going to set the frequency almost equal to the eigenfrequency now. Okay? Then this, of course, is just minus omega 0 squared. Yeah? Verify this, and then you tell me if I did something wrong here. So this is 2e squared, 3c cubed, m, which is the mass of the electron, omega 0 squared, and this is then what we define as the classical damping coefficient. It does seem like I have the same expression in my notes. So that's good. Now, we can also, which will be useful for us, write this in terms of the frequency, ordinary frequency. And then it's just, of course, 2 pi squared nu 0 squared. So this is called radiation reaction term, and it's the classical damping coefficient for the atomic oscillator. All right, that was good. Now, where were we? We wanted to use this in our approximation for the cross-section, which was sigma Thomson nu squared divided by 4 times nu minus nu 0 squared plus gamma divided by, I always have to see what I get out there, right? 4 pi squared. Okay, so if we replace this now, the one on the top, with the classical damping coefficient, then we again, for today, skip one algebraic step only here. It is actually only one. And we can write this now as sigma nu equals 2 pi e squared divided by MEC sigma divided by 4 pi squared, and then nu 0 squared plus gamma 4 pi squared. Okay, so a few things here. And this was just algebra, 2 algebraic steps, okay? Getting from there, using the classical damping coefficient, plugging that one in here, and you end up here. As you recognize, I replaced the classical here by just a standard gamma, okay? And I will come back to why I did that, right? But we have used the classical here. So now, what can we say about this? Well, this has a very specific form again. It has a different form than before, but we can write this now as sigma, and we're going to call this CL as in classical, times, we're going to call this a profile function, and that profile function we can see now is a general function of nu 0, and the damping coefficient gamma, where in our case the damping coefficient gamma has been the classical expression for it, right? So there are several interesting parts of this. The first is that this function there now, phi, okay, so now we just write short phi nu L, it's just gamma 4 pi squared nu minus nu 0 squared plus gamma 4 pi squared. This is called the Lorenz function. And this is the Lorentzian function for natural line broadening. Now, the thing is that in this, written in this way, this has the property that if you integrate the Lorenz function over all frequencies, it is normalized. That is, it comes out as unity. So therefore, you can see that if you integrate the cross-section over all frequencies in this now close to the line approximation, this just comes out as sigma CL, which is the classical frequency integrated cross-section. And that also has a fixed numerical value, which is 0.0265 centimeters squared. However, we have to add the hertz now, because this doesn't have the same units as a standard cross-section, because we have integrated over all frequencies. So a hertz comes out. This actually causes quite some confusions often when you compare cross-sections, because you cannot compare the value of this frequency integrated cross-section, of course, directly with the Thomson cross-section, for example, because they have different units. You have a frequency missing, yeah? So you always have to deal with that, and we will see an example of that when we talk about the so-called Q value of these atomic oscillators. So that's the first, and then we can look at the profile function here. How does it look? Well, it has something like this, right? Here is nu equals to nu 0, so this is resonance, right? And then we can see that clearly this has a sharp peak there, and then it, oh my God. Then this is, as you can see from my drawing, this is clearly symmetric around line center. this was even worse than I normally do. Huh? Yeah, something like this perhaps is a little bit better, tiny bit better. The fall off here is 1 over, we can call it delta nu squared, right? Or delta nu is nu minus nu 0. So the fall off is steep, but it's not at all as steep as in other line profiles we'll see later during the course. For example, from the Doppler shifting and Doppler line broadening, which is an exponential, right? That's a Gaussian. So that's the first. Now, we can also look at some further. We will keep this one here. I will take these ones out. We have the profile function there. So we want to characterize the width of this now a little bit. Now, first we can say, okay, the peak value, well, that's not so difficult to realize what that is. Even I can do that. It's like nu Lorenz, that's at nu equals to nu 0, right? So then this one just vanishes, and we just have to keep our head rate. What will come out here is, well, this pi, but then you have a 4, and then you have 2 of these. So essentially 1 4 will come up. So this will just be 4 divided by gamma. Okay? And then we're going to do a characterization of the width of this line profile. So we're going to have to choose something. So we're going to choose half of this. That's neat. Okay? So half of this value is, yeah, well, that's that divided by 2, right? And that's at some certain frequency, okay? So we'll go down here and go down a factor of 2, and then we have as much there and as much there. And then we can perhaps look at this first, how much we have there, okay? So that would be something like nu Lorenz at nu equals to some sort of nu minus nu 0, right? Some sort of delta nu. That would be 2 divided by omega. And then we're interested in that, which we can perhaps call delta nu there. So we have to, I guess, plug that in. So it's going to be something like this, right? And then delta nu squared plus gamma 4 pi squared. Okay, so we take that up, we take this up, we get something on this form, delta nu plus this one squared, and then let's move that up. We have something like gamma squared divided by 8 pi, right? So delta nu squared is going to be that one, and then minus, so this would be 216, right? And this would be 116, so we're going to have 116 left. So gamma squared divided by 16 pi squared, or delta lambda is going to be lambda divided by 4 pi. Okay, so what have we calculated now? Well, we have calculated this one, right? Okay? That's the delta. If this is half the value, which it may or may not be representative of in my graph, this would be then 2 divided by gamma, half the value. We have calculated half, but let's say that we want to take the full width here instead. Okay, because it's convenient. Then we see that this one is, what's it going to be like? And what are we going to call this? Well, we can call it like the full width of what? Half maximum, right? And that's going to be 2 times that. So gamma divided by 2 pi, and that's the full width half maximum for the Lorenz curve. Okay? So there we go. There we have a characteristic width of the Lorenz curve, which is very interesting because you can see that it is set by the damping coefficient, right? So if we want to remember this, very easy, we again go to our angular frequency, right? And then we can say that, okay, delta omega for the full width half maxima of the Lorenz curve, that's just gamma. Very easy to remember. And if we didn't find this, then we did an error. So in our case, then we can see that we actually can get a classical width of the resonance for the atomic oscillator here by just looking at the value for the classical damping coefficient, right? And that would then be delta omega full width half maximum classical is just gamma classical. Now, even more interesting, and here again I will leave for you so you can go back and actually practice this a little bit. Now, if you do this now in wavelength space instead of in frequency space, remember we have discussed this previously in the course, then you have to take into account that delta lambda divided by delta nu, right, is equals to C divided by nu squared. That's just using our standard relation, nu lambda equals to C, okay? So if you now do this, and then you do this exercise, but instead of in omega space, you do it in lambda space, okay? You plug in the damping coefficient that we just calculated, which I erased on the board, but which you have in your notes, for this. Then you find that in wavelength space, delta lambda, we call it classical, full width of half maximum equals 1.2 times 10 to the 4 angstrom. And it is a constant. So in wavelength space, the spectral lines have a classical, they had a classical constant width. And one of the reasons, well, there are several reasons why this is a very interesting result. One of them is that you can see, wow, this one is not very big at all. Huh? So if you now want to put the width of your resonance here in comparison to something, I mean, what would you put it to in comparison to? Well, the rest frequency or the rest wavelength, right? So let's work with the wavelength here because we had the number, right? Right? Then you can see that delta lambda divided by lambda, so the characteristic width of the resonance divided by the wavelengths, and then again we can take like an optical wavelength. If we take 5,000 angstrom here, then you see that this is perhaps it's easier to take 1,000 angstroms now, so we don't have to deal with so many. This is on the order of 10 to the minus 4 divided by 10 to the 3. So on the order of 10 to the minus 7. And that was for an ultraviolet wavelength. So it's extremely narrow. 10 to the minus 4 angstrom is... Now, another interesting thing, which we can already realize from now, is that, okay, now we have gotten ourselves into trouble because we sort of predict that all lines have the same width and the same strength, right? when we frequency integrated, we got to a classical cross-section that was just a constant. But there was no specific thing in there that, okay, this is different for hydrogen, this is different for carbon and stuff like that. And it's similar here. They're all of the same width. Huh? And we know experimentally, or people knew experimentally, that this was not the case. And this is, of course, where our classical analysis then breaks down. And we'll have to appeal to experiments, to quantum mechanical calculations. Now, I wanted to use these results, though, to get some further feeling of the powerfulness of spectral lines, actually, which we can do also from this classical analysis, okay? So, if we now take our omega 0 divided by our typical omega there, that's our characteristic width of the line profile, okay? Then we see that we have omega 0 here divided, and we know that this is our damping coefficient, right? And that is what we normally classify as the Q value of the resonance. So again, this just comes from the classical oscillator. And that's a way to characterize how strong, how powerful the resonance is. And this then, as you can see, we can approximate with then just lambda 0 divided by delta lambda as well, which, as we have already done, no, it has to be the opposite here. Sorry. Because, yeah, of course, you have to turn them around when it's lambda. Delta lambda, which is on the order of 10 to the 7 or 10 to the 8, depending on the rest wavelength that we get in there. So, this is to say that the quality of the atomic oscillator is on the order of 10 to the 7, 10 to the 8. And that's an extremely powerful resonance. And this is where I actually found the corresponding. Of course, we're doing this for the astronomy applications here, but I just saw this also in my in the book that I used as an undergraduate, where what they wrote about this is that the Q value for mechanical oscillators can reach values of 10 to the 3. So mechanical oscillators here would be like the friction or something when you swing somebody, like a whistle when you blow in the air, stuff like that. Now, for a church bell, we'll have a somewhat lower value of Q, so perhaps the church bell here in Leuven doesn't have that Q value, but a little bit lower. It's not so efficient. But for electric oscillators, higher values are obtained. For vibrating electrons inside atoms, i.e. antennas emitting light, that is exactly what we have done now. Q is about 10 to the 7, which is what you have here. Yes? Yes, because I turned them around, right? Yeah, it's... Sorry. Sorry about that. And this is an approximation, yeah? So there is another exercise here for you to do in the context here, which I just wanted to fill in, that if you now calculate this Q value, you can show that it is proportional to the classical cross-section divided by nu0 times the Thomson cross-section. Okay? So the way you can see this is that, remember, we had this difference in the units between the frequency integrated cross-section and the Thomson cross-section. So by calculating this value, which indeed comes out as 10 to the 7 to 10 to the 8, you sort of get an enhancement factor of this cross-section close to the resonance. Right? So, in principle, the cross-section close to the resonance here, when you take the frequency integrated value, is enhanced by a factor of 10 to the 7, 10 to the 8. And this is actually critically important for even my own research. Because one of the implications this has is that when you have a lot of photons present in an astrophysical system, so very luminous objects, I've talked about how you can actually exert a force from the radiation field. You get a radiation force. We discussed the generic forms of that. Yeah? Now, that generic radiation force can have a minimum value, if you assume again that you have a lot of free electrons, so ionized media, set by the Thomson cross-section. However, that force can be enormously enhanced for specific line transitions. And the basic reason is this. And this leads then to very strong radiation line forces. And that has, for example, one of the things that my research has focused mostly on over the years are so-called line-driven wind outflows. Because then we have that in the outer parts of very massive stars, but also from accretion disks around supermassive black holes. Then you can have a lot of spectral lines interacting with the radiation field through these line transitions, and thereby greatly enhancing this radiation force effect. So you get a real kick outwards by this. And therefore, you can launch these giant outflows from the surfaces of these objects. And that's typically what we then call a line-driven wind outflow. Line-driven because it is essentially powered by the extra force you get by tapping in to these spectral lines. Now, in practice, it comes with some modifications. It's like, wow, do you get really 10 to the 8 more? Well, not really 10 to the 8 as compared to the Thomson value, because lines can also, as we will learn, saturate. So at some point, you have reached that you have blocked all the light that you have available to you, and then you can't do anything more, right? So there are some complications, but the basic physics of line-driven winds, for example, is actually contained here. And then, of course, we had the other complication here, which was that we predicted now that we could always write this for all spectral lines on this form where we had the Lorenz function and we had the frequency integrated cross-section. But we know that not all lines are the same. So typically what we do then is that we have to revert the interaction to quantum mechanical calculations. But we can still use this. We just have to insert a correction factor here. And that correction factor, well, it's called the classical oscillator strength for, hopefully now to you, obvious reasons. So then typically we classify the strength of the spectral lines with this value. And then we can still use the same sort of expression because for a lot of cases the line profile function still comes out to be a Lorentzian. So that's the one modification, and then the classical damping coefficient just goes to a damping coefficient that we have to calculate, and that is specific for different lines. We will come back to that, how to estimate that in the next chapter. And in terms of the Q value here, well, then we would just have to add the FCL there. Okay? So before now we're going to just look at one interesting thing here. And that is that, okay, we're going to shut off the driving force. Yeah? And then we, of course, have the oscillating solutions, which is this plus gamma c dot equals to, in this case, 0. And if we write down that solution, I will just again write it down. It is in your textbook. You get something on this form here. So you can see that it damps out with a certain characteristic time scale. Okay? And if you were now to compute the corresponding energy for this system, you would see that they die out with gamma t, without the factor 2. This is the amplitude. The energy would have that. So then we can actually define a characteristic time scale for the system, which we define then as 1 over gamma. And again, if you plug now the classical values in to this, which again you can plug in some numbers, then you will get that this is extremely short, 10 to the minus 8 seconds. And that means that the lifetime of the excited state here is extremely short. In this case, it's the oscillation, once this is turned off, dies out very, very fast. And indeed, when we compare this then to the typical expected lifetimes of the strongest lines that we have and use quantum mechanical calculations, then they are on similar order of magnitude for allowed very strong transitions, typically so-called resonance transitions. Hence the name for resonance lines that you often see investigated in spectra. All right. That was it for today.